Converting the inconsistent kinetic energy of wind into stable, grid-compliant electrical power is a fundamental challenge in renewable energy. The unsung hero facilitating this transformation is the wind turbine drivetrain, a complex assembly of mechanical and electrical systems operating under immense, dynamic loads. Its engineering represents a critical battleground against efficiency losses and catastrophic failures. At its core, the drivetrain connects the slow-spinning rotor blades to the high-speed generator. This linkage must precisely manage fluctuating wind forces, amplify rotational speed by orders of magnitude, and convert mechanical torque into electrical current, all while ensuring operational longevity and minimal downtime. The gearbox stands as the drivetrain's most mechanically stressed component. Rotor blades rotate slowly, typically between 8 to 20 revolutions per minute. However, the generator requires speeds of 1,000 to 1,800 revolutions per minute to efficiently produce electricity at grid frequency. This substantial speed multiplication necessitates a sophisticated gearing system. Wind turbine gearboxes predominantly employ multi-stage designs, often combining planetary gear sets for the initial high-ratio stages with parallel shaft gears for subsequent stages. Planetary gears offer a compact design for significant speed increase, distributing load across multiple planet gears. Parallel shaft stages refine the final output speed with robust, simple arrangements. One of the most persistent engineering challenges in gearboxes is managing extreme loads and fatigue. Wind turbines experience highly variable and often unpredictable load spectra, including sudden gusts and turbulent flow. This leads to cyclic stress on gear teeth and bearings, causing pitting, micro-pitting, and eventually catastrophic fatigue fractures if not meticulously designed. Lubrication further complicates gearbox reliability. High-power density gearboxes demand advanced synthetic oils that maintain viscosity and film strength across wide temperature ranges and under extreme pressure. Contamination from wet particles, moisture ingress, and thermal degradation of the oil itself are common failure modes, leading to accelerated wear and reduced component life. Engineers combat these issues through several innovations. Advanced gear geometries optimize load distribution and reduce stress concentrations. Specialized surface treatments like carbizing and nitriding enhance hardness and fatigue resistance. Improved bearing designs, often featuring larger rollers or optimized geometries, along with sophisticated filtration and oil condition monitoring systems, extend operational life. Transitioning from mechanical to electrical power, the generator is the heart of electricity production. Modern wind turbines largely utilize doubly-fed induction generators, or DFIGs, and permanent magnet synchronous generators, or PMSGs. DFIGs allow variable speed operation, crucial for optimizing aerodynamic efficiency across different wind speeds. DFIGs achieve variable speed control by having a partially rated power electronic converter connected to the rotor winding. This enables independent control of active and reactive power, contributing to grid stability. PMSGs, while requiring a full-scale power converter, offer higher efficiency and eliminate the need for a gearbox in direct drive configurations, simplifying the drivetrain. Generator reliability faces distinct electrical and thermal challenges. Winding insulation breakdown due to voltage transients, thermal cycling, and partial discharges is a significant failure mode. Bearing failures, exacerbated by electrical discharge machining currents in variable frequency applications, and overheating from cooling system malfunctions are also prevalent. Solutions for generator longevity include advanced insulation materials with superior dielectric strength and thermal stability. Optimized cooling strategies, such as liquid cooling or improved air circulation systems, manage internal temperatures. Specialized ceramic bearings or insulated bearings mitigate electrical discharge damage, while sophisticated fault detection algorithms predict impending failures. Finally, the braking system ensures safety and control. Beyond aerodynamic braking achieved by pitching the blades, mechanical braking mechanisms are critical for emergency stops, controlled shutdowns during high winds, and parking the rotor for maintenance. This redundancy prevents runaway scenarios. Mechanical brakes typically involve hydraulically actuated disc brake calipers acting on a large rotor disc mounted on the high-speed shaft. These brakes are designed for powerful, controlled deceleration, often engaging only after aerodynamic braking has significantly reduced the rotor speed, or in situations where aerodynamic braking is insufficient or compromised. Despite their critical role, mechanical braking systems are susceptible to specific failure modes. Hydraulic leaks can compromise clamping force. Disc wear, caliper malfunctions, and seizing are common. Sensor failures within the control system can prevent timely engagement or lead to unintended activation, creating operational inefficiencies or safety hazards. Engineering advancements in braking systems focus on robust, redundant designs. This includes dual hydraulic circuits and multiple caliper arrangements. High-performance friction materials improve braking efficiency and wear resistance. Predictive maintenance algorithms analyze brake component wear and hydraulic system health, ensuring the system remains fully operational for critical safety interventions.